Back to CC 373 section 5. Now we're going to talk about simulating BFS. So this is definitely more interesting than the other. So we have this two things. So one thing is we have a queue of vertices to explore. You can think this is a queue, right? And then so oops, and here you have, sorry, it's like stuffs are blocking on the camera. So you can see that this is actually some kind of table. In real life, you can kind of think about there's a set and there's a map that keeps track of its predecessor, and then set that checks or set or boolean some kind of, I don't know, map, another map that essentially keeps track of if it was processed or not. In a lot of time, usually nodes are represented as a number too. So if that's a number, then you can just use an array that you use an index to check if it is processed or not. But if it is a letter like this, nodes are represented as a letter, then you would need a map, right? That's key as a node and then value as if it is processed or not. And another map that keeps track of its node to its predecessor. But we'll see why that it would matter so much. So here you can see this queue of the vertices to explore. So we start from S, that's our starting node. Handy, right? And then now we know that it doesn't have any predecessor, so we'll just leave it blank, okay? S is popped. So what's going to happen now? We have a T and then Y being pointed by S. So we add a TY. See, and then we have updated this information, right? SS. Then now we're going to pop T first because that's the beginning of the queue. So T hasn't processed now, right? But whenever you have pop, you need to add their neighbors immediately, right? So here you say it's pointing, T is pointing Y, Z, and X, right? And here it comes why those discover stuff are important, because you can clearly see that the Y already is here, right? And then now you're going to see this X and Z. So X and Z doesn't have any predecessor yet, so it's more interesting to see. So we are not going to update Y. You know why? It's kind of like funny pun. Because you already know that if it, like in BFS, if you think about its nature, it's going kind of like a breath, right? Breath-like. So if it already has a predecessor that have been seen, it means it is the shortest path already. Because this graph is not weighted, which means that like each edge doesn't have some kind of value associated, like associated kind of meaning or value into it. So we can just consider as they're all like cost of 1. So in this case, it'll be like where from S to Y, it'll be 1. From if you're going S to T to Y, they've actually cost of 2. So this is really important part of BFS because this graph is unweighted. We know for sure that the one we have seen must have a shorter path to get there, right? Or you can think of a kind of less number of edges to get there too if you really want to think that way. Okay, so now we don't update Y, but we did update our T and X. I mean, sorry, T and Z. It's pretty late here. So, and now we're going to pop Y. Another interesting thing. So Y, it is pointing to Y, Z, and X. So our question is, should we update this or not? One more time. So for X, we won't do anything, right? So from previously, it was T, and there is no reason for us to update, like we said, right? So there nothing happens. So from this Z, now we're going to handle this, sorry. So nothing will happen. So X will process first and nothing will happen. And now we're going to do handle Z. Now we know that Z previously was still pointing by, we already had its predecessor from T. From where? Well, like pretty long ago. From when we had T, we updated X and Z. So we don't update them at all. Right. Then now everything has been processed. Just one thing that really, and you can clearly see that there's like a cycle going on from this graph, right? So it kind of shows why process is important. Because if you already have seen, then you shouldn't go back. Otherwise, you're kind of getting to this infinite loop. So yeah, now everything is processed. And this is what it goes. And you can see resulting SPT. The easiest way to really get to this is you can kind of keep track. So Z comes from T, so the arrow will go like this. X is being pointed by T. You can kind of think it as like pointed by. So you can see like arrow X to T, and so does S to Y is being pointed by S, and then T is being pointed by S as well. So then this is how the SPT would work. So yeah, one thing really to keep in mind is that why does simulating BFS result in the shortest path tree is actually working, right? Because this is unweighted, because we won't update the one we have seen, because we already know that, because by the definition, see, by the definition, if we have seen somehow, let's say we have another cycle here from D to B, then it doesn't matter, because if we already have seen, because in order to get to my current node D, I must have explored B before me, right? Then we shouldn't update that, because the distance will be longer than what we have seen before. So that's kind of interesting idea about this simulating BFS.